Okay guys, welcome to the next chapter on serialization. I had to go shave my face and take a shower just to even attempt to start doing this thing. This chapter is going to be fairly well loaded with computer science stuff. So, without further ado, let's get started. Over here we're looking at a modified version of the guestbook contract. I called this particular one serialized because we're going to be talking about serialization. So, what I added here is two variables, messages and other data. Messages is same as in the guestbook, is going to be a vector with the prefix of v byte, and the other data is going to be a lookup map with a prefix of m byte. These are arbitrary. You can change them as you want, just keep them different from each other if you have more than one data structure being saved. I also added two extra methods. Over here we have add other. This is to add an item to our lookup map with a key and value pair. And the get other, we're getting item by key and returning a string. Now let's get all this set up. We're going to create an account to save this in. So near create account, ser.a.test.near, master account is going to be a.test.near, initial balance will be 10. Now I'm going to compile our contract. So at first I'm going to do cargo clean, and then I'm going to do rust up target add wasm32 unknown, and now I'm going to cargo build. What's this? Let's try it again. Sometimes during compilation there might be some bug that causes it not to compile right away. Okay, compilation is complete. Now let's deploy it. Near deployer wasm file is called serialized.wasm. Account is going to be ser.a.test.near. Let's deploy it. And let's call it from our postman to make sure that it actually exists. So ser.a.test.near in our parameters on the JSON. Request, send. And we have empty values, but it does exist, so this is good. Now let's make a few calls and store some information in our contract storage inside this vector and inside of the lookup map. So I'm actually going to move this to the side again. Clear. Now I'm going to do near call. So over here I'm going to call a message and save my first message, and the account ID that's going to be calling this smart contract is b.test.near. This is the account that's going to sign it. Let's go ahead and do this. Enter. Let's take a quick look here and see if anything changes on the return from our postman. Yeah, something's changed. So now we have two values. We have the state, which is recording something in here, and we have over here a different key with some value in there. Let's try to add a map value, the add other with the key value pair. So we're going to add other with the key. It's going to be key. This can be any arbitrary value you choose to call it, as long as it should really be unique, because when you specify the same key, it'll just overwrite what you already have, same as in any kind of a hash map data structure. And the txt is going to be my map value. Really original, huh? Okay, let's run this. So we saved something in here. Let's send it off. And okay, now we have two values stored here. Now we're going to go through what all this stuff is. So let's start decoding this thing. Copy this, go in here. Where's my base 64 decoder? I'm going to actually increase it in size a bit. And I'm going to paste it here and decode. Over here we see M, some sort of values, and then key 1. Let's go into another decoder where we're going to control string to binary string. Let's see. Okay, so over here we took the string and we converted it into these values here. So each one of these items is represented by an 8 by 8 bits, so by 1 byte. Let's try and convert this same string into decimals. So now we have 109, 4, 239, 191, 191, 189, and this repeats a few times. 1, 2, 3, and then there are some other values coming up after that. Okay, so the way to see it is, the way it is decoded is this. This is a decimal value of M, of character M. This 4 is how long our key is. So our key is 1, 2, 3, 4 characters long. Over here, these 139, 191, 189 are actually placeholder characters. So it's a Unicode encoding string, which uses 3 bytes for character encoding. So if we go to this map right here, and we look over here at the bottom, it's a replacement character. Let me just go all the way down. U plus FFFD, this question mark, 239, 191, 189, replacement character. Now the reason why we need all these characters stored in here, let me go back. Okay, so the reason why we have all these characters, like, so 1, 2, 3, and actually 4, is because we have total of 4 spaces of 8 bytes. So the number of characters that we can store in this key is actually 2 to the power of 32. So we have 4 times 8 bytes, which gives us 32-bit integer to represent the length of what we are storing in the key. And I'm going to actually show it to you by doing one interesting thing. So let me get the English dictionary here. This is 26 letters. Now I'm going to copy it over 10 times. So we're going to have a string the length of 260 characters total. And now we're going to set a key with which is 260 characters long. So I'm going to paste it. I'll just save some other value, and I'm going to press enter. We're going to go back to our Postman and get all these values from here. And here's our really long key over here. Let's decode it and see what it says. As you can see, now we're down to 2 of these placeholder characters. Let's decode first few characters here using our second decoder. We have 10941 and then another 2 of these characters. So now we have 2 bytes representing the length of our string, which is 260 characters long. Next, we're going to look at the binary representation of this and see if we can manually reconstruct 260 out of our binary value, right? So I'm going to search for binary, string to binary, paste the same thing, and we have binary representation here. So we have this one here of representing our character M, and then we have these 2 representing the length of our actual string, which should be 260. One thing to understand is that we have a little endian representation of our bytes in here. What little endian means is that our first byte starts on the right, so from here to here, and as it moves from right to left, the decimal digit goes up. So for example, if the number 1 was in here like it is here, this means 1. If it was in the second position, it would be 2. If there was 1 byte here and 1 byte here, 1 and 1, it would be 3. If it was here, it is 4, and so on. So this one, for example, here is 4. Okay. When it gets serialized, these sets of 8 bytes are actually reversed. So even though these sets of 8 bytes themselves are in little endian format, this one, the second byte, has to actually be in front. Let me show you what I mean. Let's say if I take this and I try to decode it into the length of our string. Let's try doing that. I need a digit converter. Binary to decimal converter. So I'm going to enter a binary number here. So remember, it was like kind of like this, right? So we had 1, 2, 3, 4, 5, 6, 7, 8, and then the next one was kind of like 1, 2, 3, 4, 5, and then 100, and then like this, right? So 2 bytes like this. If I convert it, it's 1025. But as we remember, we actually had only 260 characters in our string, right? So what we're going to do now is let's take these two. I'm going to copy them over here. And this one, the second byte in line, actually I'm going to place it in front of the second one. And now if I convert, as you can see, it's 260, exactly the number of characters that we have. This is how this one gets serialized and deserialized. So I actually have a little map here, which I created, so we can see what's what. So here's the bitmap, and I'm actually going to include it in the Git repository. So here the LookupMap that we've been working with. So we have a first byte as our prefix representation. Second, third, fourth, fifth byte is the representation of the length. So even though when we get a base 64 decode, it actually decodes into a 3-byte character, it actually only represents one set of 8 bits, sorry. So we have 1, 2, 3, 4, total of 32 bits representing the length of our key, how many characters we have in our key. And or how many bytes rather we have in our key, because if we had a Unicode character of some other language, sometimes characters use more than 1 byte. Okay, the total of bytes we can have in our key is 2 to the power of 32, which is over 4 gigabytes. I don't think you'll ever be storing something that big in a blockchain, because I calculated how much that is. It's over, for Near, for example, at the current price of Near token, it's over $200,000. So yeah. Anyway, and over here we have another one, just two examples. So one key is like 4 characters long, second key is 11 characters long, and it just shows you how it is decoding. That's serialization state. Let's move on to the vector serialization. Vector serialization is actually a bit more straightforward. I'm going to decode some of this vector stuff here. I think the first vector was this one. Okay, as you can see, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 values, all of them are unknown character. This actually represents the value of 0, so it's the first element in our list. The reason why we have 8 characters is because this is represented by a 64-bit integer, which requires 8 bytes. So this is why we have 8 of these characters displayed here. Nothing special now. Over here, I also pointed the same idea of how the vector is being serialized. So 64-bit int, denoted by UTF-8, 3-byte unknown characters. So we have one byte reserved for our prefix, and then 1, 2, 3, 4, 5, 6, 7, 8 bytes used to show our to represent our 64-bit integer in the serialized form. You might be asking, why is 1 byte represented by these 3? This actually happens when we do the base 64 encoding decoding. I don't know exactly why it happens exactly this way, but all I know is that even though it's a 3 bytes representation for the unknown character, it actually represents only 1 byte inside the serialized data. Okay, so now we're pretty much done with our serialization. I hope this was helpful. You might be wondering, why is it so important to know this? Now, when we do invoke a get methods on our contract, we have to pay gas every time. However, when we have to do things outside of our blockchain, like read data from a blockchain, we may not want to invoke a get request, because every time we do, we have to pay gas, and we might just break the bank doing it. For this reason, we can use the RPC requests and get exactly the data that we need, provided we know the key of that data. However, in order to reconstruct the key of this data, we need to know exactly how it's being serialized, because when we query this, it actually returns us the serialized version of the key, which means that on our front end, we have to serialize it in the same way as it is being returned to us from the blockchain. So we need to have exactly this string to get this specific key. Like what I'm going to do now is copy this, paste it into the request underneath this prefix base 64, and I'm going to send, and this is all I'm going to get. I'm going to get exactly this key value pair over here. This is necessary to do because if we wanted to get the whole state every time, it's going to be a lot of data, and the state requests are actually limited to only about 50 kilobytes per request. So if your return state is big, you're not going to get more values than that, and it's going to be very slow. But in order to get this key, what we're going to do is we need to encode it properly, serialize it, and get this base 64 encoded value. And then we can query it using the RPC. And in the meantime, while front-end libraries may already have this built into them, we may want to go further. Maybe we want to make some game in the actual game engine, and we need to have some sort of serialization system inside it in order to generate these kind of keys, right? Which is something that we're going to be doing in this tutorial series, by the way. So I hope this was helpful to understand how the serialization deserialization works, and we are going to be using these concepts in order to query the blockchain later on from the front end. Okay, so thank you for watching. Don't forget to subscribe, share, like, and I will see you guys in the next tutorial. Bye-bye.